Okay, hi everyone. I think this is somehow the continuation of what we have been discussing on data and data relevance and data evaluation, so it fits really nicely. I'm presenting on this title, the timing and data relevance in pull and push-based communication, together with my colleague Junya Shiraishi. I'm Pandey. I'm an assistant professor at Department of Electronic Systems in Aalborg University, and belonging to Qatar Overseas Group. This is the goal of my talk. So what I'm trying to do together with Junya is trying to understand these two important aspects in 6G systems. And we're trying to look into how we can make it more communication efficient, or efficient in every aspect, let's say in terms of energy, or let's say different metrics of latency, reliability, and so on. So we are trying to understand the interplay between timing and data relevance. And we're going to look a bit deeper into the novel paradigm of pull and push-based communication systems. And together with these two concepts, we're trying to think more on investigating new kind of challenges and maybe what kind of potential research questions could be out there, so we can solve in this novel scenario of multi-party, multi-domain systems. The general outline that tries to achieve the goal. As a background, I think I will take you back a bit more on the access side. So we'll be talking a bit about IP networks. And we already agreed some sort of that AI and machine learning has somehow impacted in transforming our existing communication systems to go beyond 5G and or 6G. So it means that it's not just beyond, it's not just trying to catch up with the latency, ultra-reliable, low latency, reliable communications, but you are also trying to incorporate new modality of information, a new kind of data set or data, for example, localization and through localization and sensing, and all these things, all these elements are coming together through collective intelligence. So how we are going to design efficient communication protocols in this kind of new setup, which was not there before. So we think that there are two key design principles for efficient communication. So that's what we are focusing on within the 6G project. So one is the timing of communications. So we talked a lot about training machine learning model, but timing for inferencing is equally important for efficient communication protocol design. So you can think of timing of communication in how and where we are going to process information. Actually, that's how we are going to translate into this timing aspect. And it could be realized in the IoT setup in the form of trying to train a machine learning model at the edge, or edge AI, let's say, or trying to do some kind of actuation and control operations over this network system. And one of the metric would be for timing would be age of information, or age of information somehow simply reflects the age or the freshness of the information. So you can think of how you are going to gather more fresh information so that you can have more accurate inferencing and also do a correct actuation and control over the system that we're looking into, right? And the second aspect is the relevance of data. And basically, this is a very tricky thing when you talk about data evaluation and data relevance, because often the relevance of data is related with the receiver's goal. So for example, these days quite popular semantic and goal-oriented communication. So you're looking into the utility at the receiver side, and or say the goal of the receiver side, and trying to tailor your transmission protocols to achieve that goal. So in this scenario here, you can see is the receiver is trying to look into some image, and there is the transmitter trying to do some semantic filtering and only transmit these kind of images. So you can somehow elevate the communication overlay that would be there in the system otherwise. Now we talk a bit about the data evaluation and timing, but how we see this interplay coming together. You see that the value of data is basically not the inherent feature of the data. So the value will not create by itself. So either you have to do some sort of transformation or computations on top of it, like say you do data pre-processing, and then it's trying to come up with some value. Or for the scenario where you have age of information, you can see that the value is coming up through the process of sampling data itself, or also it's emerging through the algorithms that we are going to use. For example, you're using some machine learning algorithms, and your data is trying to help to make a better generalization on the task that you're going to do. So it means that the value is creating in that sense. Also, the value of data would be depending on, because we are talking about the network system, so how the correlation is there between devices that are creating this data. And all of this, the relevance or whatever we say, it's the value of data, it's coming together to affect the meaning and significance of the transmitted data. So, for example, if you know if you have some strict timing requirement and you're trying to train a machine learning model, then you would be more interested in sending and sampling more, let's say, contributing piece of model updates that you can use to aggregate and try to create a better learning model so that you can accelerate the inferencing process rather than just sampling randomly, right? So we see that there's this very tight coupling between the data value and timing aspect. And these all together falls into two regimes of efficient communication that we are saying and are doing since a long time. So we say that it's the strategic pull and the strategic push. So for example, the receiver can somehow be a bit more intelligent in its querying process or sampling process and ask for only the relevant piece of information. So you elevate the compute load or let's say communication overhead. So we call it strategic pull. Also, we can also think that the devices themselves are becoming a bit more intelligent, and they can infer some of the utilities that's there in the receiver side. So they tailor their transmission plan accordingly. So they will only sample and send the relevant piece of information that will bring some value out of it at the receiver side. Okay, now I will leave the floor to Junya to go a bit deeper into some use cases scenario in this.
Thank you, Shashi. So, as Shashi introduced, there are the two types of communication model considered. One is the push-based communication, the other is the pull-based communications. So this communication model is considered separately and studied separately. But in a strict network, this kind of things need to consider jointly and need to manage the traffic of the push-based device and pull-based devices. So specifically, we consider a scenario where a base station is interested in collecting data from the push-based node, and also simultaneously, the base station needs to manage the traffic coming from the cloud. So basically, as the push-based device setting, so basically the traffic coming from the each devices. So if the device generates the new data, it transmits data. On the other hand, the pull-based setting, we consider the query request coming from the cloud to the base station. And the base station needs to retrieve the specific data by using a pull-based application, by sending the query and collecting data. So the difficult thing is here is that the base station needs to manage the different type of traffic, as shown here. One is coming from the device, the other is coming from the cloud. Also, the communication request usually is different for the push-based. There is some request, there is a requirement for the push-based devices, and also there is a requirement for the pull-based devices. So how can we manage this type of work? So the important thing is the medium access control. So we consider a frame as shown in this figure. So basically, each frame consists of two portions of slots. The one is the slot for the pull-based communication. So in which the data is collected in a scheduling-based manner. On the other hand, the other slot is for the design for the push-based communications. So obviously, we can see that there is some trade-off. If you assign a longer period for the pull-based communication, so you can get the good performance for the pull-based communication, but you need to sacrifice the communication for the push-based communication. So basically, we investigate this basic trade-off in a single frame setting. So this is the basic result. So this result shows that the maximum traffic that the system can support for the pull-based traffic and for the push-based traffic. And this is the different time. We consider the different requirements for the performance requirements for the pull-based and push-based communication and the communications. So basically, this figure shows that if you try to if you try to support the push-based communication, so you can get the good performance for the push-based side, but you need to sacrifice the traffic for the pull-based side. So basically, we can see that the basic trade-off here. So we can see that we need to design a macro protocol efficiently considering this type of requirements. So this is the basic pattern. Sorry. So basically, the second thing is that related to data relevance. But so we aim to reduce the we aim to achieve the high energy efficiency of IoT nodes, serving the 6G IoT networks. So specifically, when we consider the scenario where an edge server is interested in retrieving a specific type of image that the IoT device is observing. So IoT device is observing a defined data. So if you just collecting data, if you collecting all data and with respect to the context, so basically you can get the which data is relevant or not at the edge server side, but it consumes a lot of energy for collecting data. So in order to solve this problem, we have introduced a framework called the tiny AirNets. So basically, in which the edge server first transmits a tiny machine learning model to the IoT devices for subsequent semantic query. So the IoT devices store this tiny machine learning model, and this guy utilizes this model and to evaluate the matching score between the observed image and the queried image. And we can see that the IoT device can get some relevance score for each image. And in this case, the image I3 is relevant, so the IoT device transmits only this image and suppresses the others. So basically, we can reduce the energy consumption for the communication, but it needs to sacrifice the energy for receiving a model and for the processing first. So the question is whether it works or not. So we consider a specific energy model considering the communication and the energy model, and we evaluate this performance. So this is the basic result. So the horizontal axis show that the number of images, and the vertical axis show the energy consumption ratio between the baseline scheme and the now proposed scheme. For the baseline scheme, we can just apply that basic offloading scheme in which each device does not compute anything and just transmit the raw data. And if the eta value is smaller than 1, which means that the now proposed scheme can benefit than compared to the baseline scheme. So the basic result here show that, so if the number of images is smaller, then we cannot see any gain for introducing our scheme because the receiving tiny machine learning model and the processing requires a lot of energy, so we don't know what to introduce this method. But as we can see that if the number of images becomes larger, so we can reduce a lot of energy compared to the baseline scheme. So we can see that the specific application that could be applicable for our scheme. So now we conclude our talk. So basically, we have discussed the key design principle for 6G IoT networks, timing and data relevance. And we have developed the communication system in coexistence between the device operating with pull-based and push-based communication. And finally, we have introduced a new pull-based communication framework to retrieve the relevant image with high energy efficiency and high retrieval accuracy. So we have some relevant work here, so if you is interested, please think about it. Thank you very much for your kind attention.
Questions?
So given the age of automation, how do you see its role with in context of machine learning? I'm struggling to actually contemplate how that would be. That's essentially terrible, not just the two of you. I mean, what do we do with we drop inputs? How does that affect the performance of machine learning models and everything else? Right? What does it mean?
I missed the first part that you said.
No, so just the fact that eventually we're going to start dropping things, let's say. How does that impact the models that we have, which normally don't say drop anything, we just don't feed as much as we can?
Okay, yeah, maybe I can.
Fine.
Yeah, so usually in machine learning we say that the more the data, the better. But actually, what I think, and based on some of the works that we did on data evaluation, we feel that not all data are good. So there are good data, there are bad data, and there are not so good data. So what does that mean? So they are good data, that means that they are contributing in bringing some value out of the algorithms, which we showed just now. There are bad data, that means there has no relation to the task at hand. So basically it will just maybe play a role of kind of an adversary to the learning model. and not so good data are kind of data that are somehow correlated and combinatorial. So it seems like you are adding more and more data, but they are basically not adding up any utility in the performance of the model. So I think we have to somehow investigate into this advanced statistical tools and methods that's there out. Let's say for under the domain of explainable AI, for example, you can use some kind of static methods which tries to figure out the marginal contributions of the inputs on the outputs, or because maybe it's so expensive, you can try to go for some kind of approximation methods, and there are several works on this. So I think that would be the direction to see. Yeah, and it's a very complex topic. So data value is a very difficult topic in itself. So yeah, that's my thinking.
So somehow also we can consider the data relevance, but the receiver side does not need to collect every data, and some data could be interesting. So in that case, if you don't need to consider all agent information, so you just need to consider some specific data, AOI. So in that case, the machine learning model could be useful to filter out the irrelevant data, and just collect only the relevant data by using this.
In general, I tend to think you guys just made our lives a lot harder.
Yeah.
But it's great research, right?